Boom. Okay, cool. So welcome to the review session. Hope everybody's having a fairly okay day. Let's just talk briefly about what we've covered between exams 2 and now since exam 2. So rigid body motion, we have angular kinematics, velocity analysis, and acceleration analysis. So by angular kinematics, we mean instead of just x, v, and a related by t, now we have theta, omega, alpha related by t, right? So there are parallel kind of things going on right there. Corollaries, I don't know, whatever. And then velocity analysis, which we knew we could do by vector math. We could do what I call the 3-diagram method. Some people call it the relative motion method. Some books refer to it that way. And along those lines, you can also use that using vector triangles, right? That's possible. Velocity triangles, and then ICR, right? So that's like subcategories within there. And then we just did acceleration analysis. And some classes might have also done Coriolis acceleration. Did you do Coriolis with sliding things? Well, we'll look at that briefly. But I didn't. I decided to skip that in my class. I did tell Dr. Orlip, so I'm not sure if he did it or not. He skipped it. Good. So we're on the same page. And so good thing to see where the equations that we're dealing with are from in this little range on the equation sheet that I provide with the exam. And so you can reference while you're practicing for the exam, like because you want to practice like you play. So if you're going to on the exam, all you get is this equation sheet in your calculator. Make sure you're using that, and so that can help with some of your comfort zone. I have old questions from the Coast Guard Academy that I post and provide out there. I often have to make sure that there's this disclaimer. This was under for 50-minute exams instead of 75-minute exams. So sometimes we might have wanted to cover more ground, so we might make the equation, the problems easier. I'm just providing them for your benefit, for your help, but not as a telegraphing of, if you know exactly this, then that's what you'll have for the exam. So this is angular kinematics type of idea, type of problem. This is velocity analysis, and students often ask, and will generally be true, will you tell us what method to use? That's a good question to say. Hey, will you? I generally will tell you what method to use because I specifically want to be able to measure whether you're able to do it. Right, that's so. But not all the time. I don't think this one is giving you a clear use ICR or vector method or vector math, but often that would be true. Acceleration problems. Quite often you have to do a velocity analysis to do an acceleration problem. Most of the time, professors will give you the velocity analysis, so you don't have to do the velocity analysis. So make sure you don't waste your time doing it if the stuff is provided, right? Read the question thoroughly. Don't just jump into it and start doing it. But generally, in a problem, you would have to do it. So most of the time, a professor will give you what the angular velocity is. And the reason why you have to do a velocity analysis before an acceleration analysis is specifically so you can get the unknown angular velocity. So if it's given, make sure that you use it instead of wasting your time doing part of a problem you don't have to do. More angular kinematics. So here's I want to leave these for you to be able to practice with, right? Because I will be posting in my class and also those registered onto the Blackboard site for the recitation. They're available there. I think Dr. Orlip also does it as well. But I usually try to hold back the solutions so you will. Now, I know that temptation is there is just to take a peek, right? So just pull back as best you can. Don't take a peek, and look at work out the problem all the way through, and then and I tell you that's like the secret to being able to get better and better at doing these problems. All right, so here are the bunch that are posted, and then I have some additional ones. All right, so here is additional ones that we could go through now, but I will say some of these are problems out of a book. So a lot of times they're harder than what the exam problems will be. That's a good idea. You know, like lift something that's too heavy, and then once you lift the thing that's not quite as heavy, it seems lighter by some extent. But it can also be overwhelming. So here is a collection that I've taken off of MUST, the Missouri University of Science and Technology. These were former exam questions at another place. So here you have, and I have provided the link in various locations, and also you could just look it up. This person, actually, I think several professors have left these over, and they're like 10 years old or even older from various exams. So there's lots of problems. So I suggest we try to go through some of these as our review session, if that's all right. Unless there's a particular problem that you want to see from a homework or something to get things straightened out. So what's up? What would you like to do? This problem? Let's do this problem. I think it's going to be easiest to be able to record this, because I looked at the previous recordings that I did in this room. I'm not sure what Tori has done. They can, I think using the, let me, not going so well. I better get your head straight. I thought the green tea would help. I'll use the document camera. That's the word I was looking for, document camera. It escaped me. Tragedy getting old. Not that bad. We'll expect less out of you if you're at a certain point. All right, so we're doing this problem right here where we have a piston, and actually this looks identical to a example problem. Actually, now that I'm looking at this, I think I did this problem. That's all right. Let's pick it apart and think our way through. Talk about what features. Talk about our mindset, what we're thinking about as we're doing it. In here, and this is given to us as 30 degrees. This one over here. And one aspect, let me see quickly. Yeah, you got to be careful sometimes when you draw something, or you might, when you look at something too quickly, you might assume that thing is right underneath this thing. But if you do a little bit of looking at this, you'll see that since this is 60 degrees, this is also 30 degrees right here. And you see that this one is longer than that one. So that does not line up directly underneath that. All right, just it's sort of a little minor thing, but worth paying attention to. We don't want to fall for little traps. I don't think I'd take a lot of points off of somebody that just made that quick little error looking at the thing, but it is worth notably. So I'm going to kind of draw just a little bit over to the side. I don't know if I quite did it. I guess I kind of did. So they said this was 60 degrees. And this one, they didn't do a very great job of labeling this, and neither did I. 200 millimeters, and this is 150 millimeters. C, B, A. I know you wouldn't do any of this during an exam, but I find this helps me think through. As I'm drawing the thing, maybe it's just me because I'm used to doing that kind of thing, I kind of start thinking about the features that I'm looking at. And the problem says that the bar here has an angular velocity of 4 radians per second. Oh, there's the, okay, I didn't see it. It kind of escaped me there, so. I'm going to draw it right down there. And that's going to be omega AB equals 4 radians per second. All right. And this one says to use relative velocity. And by that, they pretty much mean the 3-diagram method. I'd also caution, when you go to that website for MUST, if that's what you decide to do, he uses shortcuts. I wouldn't go with the shortcuts. I would just use those solutions so that you could compare with what you did. Not to memorize, do it this way. He does it like in 2 steps. And you're like, oh, wow, okay. But you won't be able to do it in those 2 steps because he's just simply like skipped a bunch of things, and yeah, it just don't think, okay, that's the way I'll do it. I'll just memorize what they show here, and you won't be able to do the same thing because it's just, I don't know. I'm not judging the person, but they're not here, so I guess I could judge the person, but I just don't think you would do. So the basic first things that you would do looking at a velocity problem like this is first get the velocity of B, because that's like low-hanging fruit, easy to do. I like redrawing. You wouldn't necessarily have to redraw it. I think there's a certain amount of helpfulness in doing this. We redraw that part right there with our omega AB, and we see that here, I think I did a pretty okay job of making that 60 degrees. It's not great. At least it ain't 45. You want to avoid the 45. Kind of lead you to thinking that it's right there. So, so the 60 that's right there is matched right there. That right there and this right here are both 60 degrees. And so here's going to be your VB, and that's going to simply be omega AB times LAB, which is going to be our 4. And is it worth changing to meters? You can keep it in millimeters. We'll keep it in millimeters. Why not? 150 millimeters. And then off the top, I should have brought my calculator, but I think that's going to be 600, right? Millimeters per second. And so now the next thing to do is to draw this piece 3 times. So I'm going to use my handy dandy ruler and come down. I kind of wish I made that a little too much like 45, at least to me it looks that way. So I'm going to draw 3 of them. I'll raise the thing up here in a second. Yes, ma'am? Again? You could definitely. But at this point, I was going to try. This is sort of the routine I kind of stick with at this point. But you totally could break it down at this point into a y component and an x component. You could break the VB into it right now if you wanted to, right? So we could have right here that guy and that guy. So you'd say VB x, and they would say in this case, if I stick with the 60 degrees instead of turning it into 30 degrees, it would be the 600 times, what would that be, the sine of 60 right there. And then we could also have the VBY downward of 600 and cosine. But I'm going to go ahead and put it down over to here. To start with in this one. But no, you're totally right. You totally could do that. 4 times the 150. The omega AB times the length 150 millimeters. Okay, cool. And now, so we apply the things that we know, which are going to be right down here. One of the tough things in this particular one is we don't want to, the angles still are a little challenging, right? So I kind of like what Natalie said. Maybe you do want to do the vertical one and the horizontal components of that right there. Not a bad idea. Stick with this right here, but it's an option. There's nothing wrong with that. Here, we know that the velocity has to be horizontal because it's constrained by this piece right here, constrained by this channel or cylinder, if that was riding in that. So I'm going to put it right in here. Now, you could go ahead if you wanted to and guess which direction, either left to the right. You're kind of if I leave it blank, that's kind of almost the same thing as guessing that it's going to be positive and to the right. So I might as well draw it right here. But recognize we might get a negative sign. So this is going to be our VC. That's our goal, is to get VC, probably. Unless they asked, yeah, they want the velocity of the slider block C. So that's what our goal is right here. And then this is the one that we know, VB. So our main idea here in the relative, they're calling it the relative velocity method, and it really is to put VB in both locations on the second diagram, because that's the translational one. Right there. And recognizing that it's going to be, we're going to break that VB in a moment into two parts. And because the VB was the reference one, we're going to pin there, and now we're going to be in pure rotation. So this is the pure translation, this is the pure rotation. So this is going to be the relative velocity one. That's where it gets its name, the relative velocity method. So we're going to have this line right there, and I'm going to choose this as positive. It's going to be omega BC. And I like to write down that I guess. Kind of a reminder to myself, or even to just, my professor, that I didn't know, but I guessed. And then I'm going to look for minus signs. And so this is going to be the VC with respect to B. And as a value, VC with respect to B, that's going to be omega BC times, I'll call it LBC. That's going to be the 200 millimeter dimension. And so now what I want to do is write out the main equation that we're really focusing on. So we're writing an equation for this unknown spot right here, which is a vector. VC is going to be equal to VB plus VC with respect to B. That with respect to, meaning that this is the reference. So here is the motion of C with respect to the reference. And when you put them together, you will get the motion of C. Now we have a strategy we can run through to solve the unknown. I should have maybe also along the way emphasized a really challenging aspect of this. Like the most challenging aspect, it's getting the angles right. So one of the reasons why I want to avoid the 45 degree, sometimes the problem might be 45 degrees, but if it's not 45 degrees, don't accidentally make it look like 45 degrees, because that would be one more challenge to throw in there when you try to find it. And so it's going to be, okay, so it was given, the angle was given as 30 degrees right here. That's not typical to measure from the vertical, but that's what they gave us, so let's stick with it. And so that's going to be this angle right in here, right in there. And if you'll note, that will be the same angle as this angle, and I was fortunate enough to have drawn it so you can see that the acute angle, or the smaller of the two angles, of the complementary angles, that should be the one that matches. If not, what I like to do is to take something with a 45 degrees right here. I mean, not a 90 degrees. Something with a 90, I was so used to saying 45 degrees, it just slipped out. Something with a 90 degrees in there, and then look and see, like, if I close down this angle, does that angle close? Yes, it does, right? I know, this is, but maybe this is easy for you, but that's the part, a lot of times, that I get wrong. Then I get and you'll get the sine and the cosine wrong of the thing. And sometimes a grader of the thing won't just recognize that you just made a little trip, you just made a little mistake. It wasn't that you didn't know to do the thing, you just got it backwards, but that doesn't, it looks like the same thing sometimes to someone grading the thing, so just be aware. Try to take a pause when you get there, make sure you do this right. Oh, so this is a good question, because in this instance, we're just dealing with the magnitude. All right? So we're not doing the cross product math. All right, so I didn't put a vector hat on top of anybody there, so that's why, that's my out. Right, I can. But if you're talking about vectors, yes, absolutely, it's going to be correct. So anyway, okay, so right here is going to be the 30 degrees, and right here is the 30 degrees. Okay, so now we're golden. Our solution strategy, our main goal at this point, our main goal is to find him. He's an unknown, but so is this. So we need to get this somehow first. And we were lucky enough in the setup of this problem that this thing is completely in the horizontal direction. So we know in the vertical direction it's going to be it's going to be 0. So let's do that one first. And so we go in the y direction. That's a y, not a g. Wider. And we take a look, and I break this guy down into 0 because he has no y component equals, here's going to have a negative component, negative VB, which we know, I'm going to use numbers instead of symbols. We'll go 600, but not 600. Okay, don't stop here. Lots of students do this. We only want the y component of this. So what Natalie had said before might have been a good strategy to go ahead and break it down immediately. This right here, in terms of angles, this is the 60 degrees they gave. We'll go ahead and use that but it looks like it would be easier to use 30 degrees for the thing, but let's make it correct for what they gave us. 60 is going to be the cosine of 60, and I made it negative, right? So it's going downwards. It's the adjacent to this angle right in there, that way right there. So we're going to do cosine of 60. Sorry, my brain just, that doesn't happen a lot lately, where I just, all of a sudden, I know what I'm doing, and pencil just decides to do what it wants. And then we also look at this, and we went, this is going to be negative. I could write VC with respect to B, but instead I'm going to replace it, and that's the reason why I wrote this up over here, to say, I know this is going to be equal to this, so I'm going to go ahead and write that in there. Wouldn't be wrong to solve for the magnitude of VC with respect to B, and then to solve it from over here. I'm going to replace that LBC with the length of this, which you'll recall is 200 millimeters. And then be careful, don't stop here. Easy to forget. This is only in the y direction, right? So we're going to take, and in this case, it's going to be the opposite of this mouth of this thing, as I would call it, the sine of 30 degrees. All right, so all of a sudden, all right, we're going to get a number here in a second for omega BC, but notice what we're going to get. It's going to be a negative number. It's because that's because we guessed wrong. It's actually going clockwise instead of counterclockwise. It's all right, but at least we knew. All right, so 600, I could probably do some of this in my head, but I'm not going to. Cosine is 0.5. Cosine is 60.5. I knew that, but I didn't trust myself to know it. All right. Divide by 200, and then divide by the sine of 30, which should also be 0.5 divided. All right, so I get 3 radians per second. Wonder if that's the right answer. I don't know. Could have made a mistake. I don't know. Let's go to the x direction here. Xter. And as written up above, right, I want to match my equations to my diagrams. That's their whole purpose. Say VC is equal to, all right, and in this case here we're going to go 600 is positive to the right. And it's going to be VB, which is 600 times the sine of 60, because it's opposite from the angle. Now here is, oh, I should have done this, sorry. Should have been a negative 3. I said it, but I didn't write it there. And then lastly on here. Now here's a little particular thing. I think it's going to help me to start out by using the sign of what this is on the diagram. So it's minus, and then I'm going to replace it with the omega BC, which is minus. I know that seems a little silly, but when everything's said and done, it helps me keep track when I guess I'm saying that right. It helps me with the acceleration one probably more often, because I had to make a guess on that part. And if I have multiple links onto something, and I don't know, I don't want to make this too complicated. You wouldn't have an exam problem like this, but a lot of times in a 4-bar, you'll have two angular accelerations you don't know going on at the same time. And to be able to keep track of the signs, it's best to be kind of systematic about it. So you make a positive guess on both of them, and then once you find one of them, plug it back in the right way. So hopefully I didn't make it too complicated. But here we go. This is going to be the cosine. So did I do that right? I think I did that right. Cosine of 30. And I didn't write down what the answer was. I was going to do that. I had the best intentions, but I didn't. So it's 600 times the sine of 60, which I don't have memorized. That's like 519.6. But now we're going to minus, so we're going to add. So we have, okay, so that's going to be 600. 30, the cosine, times, so plus. All right, so we get 1,039 millimeters per second. And if we're going to answer it, if they ask for velocity, you got to have a hat. And it's got to have a magnitude, and it has to have direction. You have to have all those things in order for it to be a velocity. Otherwise, it's just a speed. Just the numeric value, maybe. So if we got rid of the arrow, it just becomes the speed of the thing, if you don't tell it what direction it's in. All right, we could also do this in vector math if you wanted to, or we could try another problem, or use the ICR on this. We could do all three. The ICR is pretty easy to do on this one. Is it a right triangle? Let me see. I feel like I have another page in there. It doesn't really matter. But I believe so. Yeah, right here. Took us an entire. Is it? Oh, no, okay. That's because I'm using the camera function on here. Yeah. Thank you, though. And I'm using the video camera function on here because if you use the camera function, there's always this little square that jumps around all the time, drives you a little nuts. That makes you think that because it wants to focus on something. A student pointed that out to me. Really appreciate that when that happened. Okay. So I want to take a look at this. Let's see what's the best way to put it so you can see both things. We'll go here side by side. So by the way, okay, so first off, I would prefer when you answer a question about the ICR, I don't care if you sketch on top of the thing I gave you, but I don't want that to be the only thing that's on your page. So redraw the link you care about someplace, and then so you can label it effectively. So it's not hard to figure out what you did wrong if you do something wrong. It's like, if you did something right, that's totally cool. I'm like, yay! I'll even write yay next to it. Hopefully, I'll write a lot of yays. I'm celebrating on your behalf. I'm celebrating for everyone. It's happy. So just redraw the thing like I'm about to do. But when we're first looking at the problem, we could kind of like make a little sketch to ourselves and go, oh, look, I should probably do Socratic thing. No, right now. So first thing we go right up to there, and I'm about to be mean. Right there, right? No, I'm a liar. That's the wrong spot. I fell for my own I didn't fall for it. Actually, I kind of did for a second. I kind of was like, oh yeah, it's right up there. That's the ICR. Is that the ICR? No, it's not the ICR. Because you need to draw the line from here down. Right there, and where this is the ICR for this problem. Do not fall for the, I'll draw it. This line, although dashed, and I often will use a dashed line, is not this is the line of where the thing moves through. This is the line of the velocity. The velocity is moving through there, and we don't connect that. That's no. So they're down here, and this is one of the reasons why that I was mentioning. You had to be careful looking at the piece. You might mistakenly think that was right underneath there, and that was the ICR. By the way, it could be if it was only 50 millimeters longer, right? Because this thing would be right there, because this is 30 degrees right here, and this is 60, so this is 30 right there. So it's like I'm going to get it wrong again. It's an isosceles triangle. Did I get it right? Why is that like something that I can get wrong all the time? But it's an isosceles triangle. It's got the same legs. Right? Nobody's giving me a nod. And just give me some validation. That's all I want. Just yes, no, yes, no. Okay, never mind. So we could draw the thing. Well, yay, we got the ICR. Not too bad. Not too difficult to do. Little geometry action going on here. Let's see. I can kind of make that little parallel there and draw it out. All right, so here is our line, and then here is our other line. And this one isn't so bad. Now we have to start looking and thinking about, let's see, about the dimensions and the angles. Let's sketch over this lightly. This right here was given as 30 degrees. This right here was given as 60 degrees, right? That was the original problem. So now you start using your geometry rules. We would know, well, first off, that right there has to be 30 degrees, right? These are two parallel lines, and we've drawn a diagonal line across them. So there's 30 and 30. We also see that this right here is the complementary angle of the 60, so that has to be 30. Right away, we recognize that must be 30 and 30 must be the equilateral triangle. You can also see that we have 30 and 30 equals 60. So in terms of the 180 degrees that you would have, all the angles inside a triangle have to add up to 180 degrees. We know that this is 120 right here. And we could bisect. We could also just look at it and say, oh, this must be 60 and 60 right there, right? Many ways we could pick it apart, but we want to feel comfortable with that. I wonder sometimes if people aren't comfortable with it. There was someone who made this, and I try to be careful not to hurt anyone's feelings, but I would, there was somebody that mentioned not too long ago that said, this generation, right around the time that COVID hit, they were online for like geometry class and trigonometry class. So they might not have learned it like they were supposed to, and they might be hiding the fact they don't know how to they're not comfortable with certain things, and it's not their fault at all, but, under these circumstances. And you don't have to voluntarily tell anybody, but if that's you should probably go, talk and ask, let somebody know and help you through to fix that, to get more comfortable, because it's not anything to be ashamed of. I'll even throw something out there myself. I had a hard time reading when I was in high school. I didn't tell anybody. I kind of hid it away. I couldn't really read a book. I kept reading the same sentences over and over and over, and it didn't take inside my head. Someone helped. I eventually asked somebody, and they helped me out. Just little hurdles like that. Don't be ashamed if there's something like that. So if they got something wrong, and I go too fast along those lines, you don't have to ask me. Just mention to somebody, hey, could you help me kind of until you feel comfortable with it. I just want to point that out because it came up in a conversation with another professor the other day. So anyway, we know the velocity right here. It's coming right there. And boy, that looks like it's in line with that. Got to be careful not to make those things look like they're in line with each other. But this is, this right here should be is a 90 degrees, right? So that should be VB, which will say that we know. We got that on the we would get it in the same way from over here, right? We got it right here. Let's say that we get that. But now we labeled the things that we know. So we have that dimension right there. We don't even need to do any trig or anything. We could just recognize that it's an isosceles. So whatever this length is right here, this RB with respect to ICR is going to be that same length. So that's going to be equal to 200 millimeters. And then also, right away, we can see that if this is the ICR, this is rotating about this way right here. That would be your omega BC. And then omega BC is going to be equal to VB over RB with respect to ICR. So 600 over 200. And kind of nice, we can confirm we got the same thing. We also notice that it's clockwise. It's going to be radians per second. We can also see from that direction that this thing is going that the velocity right here, let's make it perpendicular, BC. And now we need to know this dimension right here. Well, we could do it in a bunch of different ways. I think the way I would like to do it is to half this triangle and maybe find, use the cosine. So I'll get the adjacent, I'll take the hypotenuse, multiply it by the cosine of 30 in order to get this. And that's only 1/2 of it, so it's going to be 2. So I would say RC with respect to ICR that's not the only way we could approach the thing. One thing you got to be careful not to do is try to take the square root of the sum of the squares. Doesn't apply in this case because there's no 90-degree angle in this triangle, right? I think I misremembered that, like when I first started teaching again after 17 years of being an engineer, and all of a sudden trying to teach something, and I'm like, ooh, totally forgot that the law of cosines even existed. But anyway, we're going to take 2 times that length, which is 200, times the cosine of 30 degrees, because I'm looking at this angle right there. So that'll get me this length, and then the 2 should be put the thing back. So if we have 30 times cosine, 200 times 2, and so I get 346.4 millimeters. So if I want to find VC, I take my omega BC times R C with respect to ICR 3 times 346.4. I'm hoping, fingers crossed. Yay! 1,039.2, but I'm going to leave it out for sig figs, millimeters per second. Good to be confirming on the thing. What would you like to see next? You could do the vector math in this. I don't like the vector math all that much, but it's okay. I'll get over it. I'll learn to deal. Ha! So my last name is Deal. So I hate that when people do that, but I do it myself. So there you go. So, I'll just keep talking. Just when I can't stand silence. That's what they said on my report card under conduct in 3rd grade. I know my mother kept my report card. Oh, Natalie, thank you. Absolutely. Acceleration problems can take a long time, so can't make the most complicated ones. Got to make just find the right amount. I do think, this is an ICR one, right? Was this an acceleration to determine the angular values? Oh, here you go. This could be a challenging one. I don't remember how to do it, but what's your thetas? Your thetas are 60. What do you think? This one? Well, in terms of types of problems, generally speaking. All right, so it's I usually try to keep it to 4 problems. I measure, and if it's too long, I'll do 3 problems. But the things I want to get out are some vector math, some ICR, and some acceleration, right? Vector math, acceleration, and velocity, and then, but the vector math could be one of the velocity ones, but I also want to see 3-diagram method. So I usually make it some combination of those. And then the 4th problem, sometimes I will ask a fairly low budget angular velocity, angular kinematics problem, where it's kind of like the stuff that we covered in the first 3 classes, where you're doing constant acceleration problems. Usually, well, so far never, where you have to use integration, but you could, right? That was like a potentially thing that you would want to do, right? So, well, let's take a look at one of those after the acceleration problem. So. And once again, it's all, the whole thought process I have in writing an exam is I want to measure this, and I want to measure this. I want to make it challenging enough that it measures whether you could really do it or you're just faking your way through it, but not so hard that it's punishing. It's got to be challenging, but not punishing. Don't know exactly where that line is, but I try to find it. All right, so it's going to be sort of symmetric about, I guess I didn't need to write that first. Something like that. I didn't do a great job of this. And we'll just have to be what it is. It's not bad. You know what this looks like to me? Anybody? It looks like it's started to draw a Van Halen logo. I'll point that out. Have I mentioned how much I love Van Halen? I don't talk about Van Halen enough, do I, in class? Should have a whole class dedicated to Van Halen. Greatest band ever. Greatest guitarist ever lived. Yeah, I know. Jimi Hendrix is a great shit. Somebody will bring up Yngwie Malmsteen and I'll laugh at them. He played at the Katharine Hepburn Theater. I can't believe Yngwie Malmsteen played at the Katharine Hepburn Theater in Old Saybrook. It seems weird to me. All the old, stodgy old Saybrook patrons, you know what I'm talking about. Yeah. The old people with money. And they listen to blues artists and they all sit here, this was some fine blues music we heard tonight. And Yngwie Malmsteen played in there with a wall full of Marshall stacks. Let's see that. Let's see, the input. Oh, no, okay, so this thing is, so this is a good problem because it's kind of going backwards. Oh, it's also a little bit too much. We did an example like this yesterday, yeah, so. But I'm going to do the velocity analysis too. There you go. I think we probably did as well there. I think we're all set, and this is supposed to be 60 degrees, and we're trying to find the angular. So let's see, I didn't label these things. B, C, and D is A. And find omega CD and alpha CD. Anything I miss? They did put an X right in there, but you don't need that. Okay. All right. So velocity analysis first. Let's see. You could think of this as being just like a piston and crank and connecting rod situation right here. But now this thing is the piston. So we're going to have a velocity that comes out this way right here. This guy is just a rocker, right? He's in pure rotation. So this is the piece that's going to be in both in translation and rotation. So we would need to do, if our life, it says absolute motion analysis. So I guess we should probably do it for both. Yeah, I was going to go ICR, but you could go ICR quickly in this, noting that at this spot right here, we go down to there, and we're down to right there for that linkage, and we can see that we're rotating clockwise. I mean, just because someone tells you to do it, in a particular way doesn't mean you can't use the ICR. It doesn't stop you from doing it. You can find it quick enough. You can kind of see which way that it's going to move right there. Because you know that this thing is going to have a velocity which goes out that way right there. So I'm going to break the rules. I'm going to do the ICR part of it first. So let's do, I'm going to draw the ICR over to the side like I said that I wanted you to do, because I should probably be keeping, I might cheat a little bit for that. So in looking at this piece, this must be 30 degrees right there, right? You do that in a couple different ways. Here's your right triangle, so that's 60 degrees. This must be 30 degrees. This must be 30 degrees. And then, therefore, this must be 30 degrees. This is practically the same problem we just did a second ago. That must be 30 degrees. So this ICR right here, this, let's see, I didn't label these. This is C. This is B. C. So this must be R, C with respect to ICR. And this one first. It's going to be RB with respect to ICR. That's not that bad. So we know what VB is. Okay, so to find RB with respect to ICR, we do that same thing that we just did. These angles happen to match this time. So we can go equal to 2 times, what are these, 300 millimeters each? 300 and 300. 300 times the cosine of 30. 600 wouldn't save me a minute. 519.6 millimeters, and therefore, while we're here, we might want to point out that we could just from observation, this had to be the same length as that, which is 300. I'll put it underneath there, 300 millimeters. So that right there is going to be omega BC. And so we know VB, which is equal, I made a mistake. Sorry. I got my arrows wrong. No, and you didn't tell me? You figured I'd figured it out eventually? Okay, cool, thanks. So that's supposed to be going that way. Look at me, I tell you not to erase, and I just erased, whatever. Generally, don't erase. I mean, if you want to fix a mistake, go ahead and fix a mistake, but don't spend a lot of time erasing things, especially if I could possibly give you some points for what you wrote. All right, so you know that VB is equal to VA, so just because it's the same rod. So that's going to be 8 meters per second. All right, so I guess we'll make that into millimeters per second. But we can see that means if it's going that way right here, pivoting about this ICR, it's going to be that omega BC. And that this direction is going to be going right there. This is your VC. So anyway, we'd have omega BC can be equal to VB divided by RB with respect to ICR. 1,000. So make that meters into millimeters. And divide it by 519.6. 18.6. 8. 1, 2, 3. Divided. 15.34. It's 396, so 40 radians per second. Sneeze, bless you. All right. Oh yeah, and now we want to go back over to this guy. So this is, so if the velocity at C right here, velocity C. So here's going to be our, have a good weekend. Wait, I guess CD. All right, so we could find. I never got VC, did I? VC is going to be equal to that omega BC we just got times our RC with respect to ICR. So that's going to be 15.40 times 300. So 4,619 millimeters per second. And then, so that's the value right here onto this. I don't know if I needed to do that thing, right? I just did. But if you want to get omega CD, that's going to be equal to VC over L CD, which is also 300. Yeah. So that makes it a little confusing right there, right? So we're going to divide by 300, and so we're going to end up with the same. But it kind of makes sense on one level because there's symmetry right there. One is going to go counterclockwise, the other one's going to go clockwise. Once again, by the way, I would have given you this angular velocity so that you wouldn't have had to do all the things I just did, right? Because I would be testing ICR in a different problem. I could just make them into one problem, but then some people would get stuck and then never get to the other problem right there. That's weird. So anyway, I could just do this in my head, right? 619 millimeters per second divided by the 300, and I should be getting 15.40 radians per second. But you can see that this one's going counterclockwise and this one's going clockwise, which makes sense that they're moving in opposite directions from each other. All right, so the acceleration analysis, we could start already from here. We already know, we can find an acceleration from this same diagram, and I usually do that right here. I just go ahead and put it right onto here. And this is going to be the acceleration of, I guess I could call it c with respect to d in the normal direction. Because I know this angular velocity, I can find that component of the thing. It will have another component along this line in the tangential direction. We don't know whether it's going that way or that way. I still think it's a good idea to guess that one based on positive, right? So as a positive one, that would be an alpha CD that we could draw onto there. And that's going to be a guess. By the way, I don't think there's anything that says this angular acceleration is going to be the same as for this piece as the other piece. I can't guarantee that, but let's just assume that let's not assume that they're the same, just because the angular velocities were the same. All right, so this acceleration of c with respect to d in the normal direction is going to be omega CD squared times LCD. So that's going to be 15.40 squared times 300. Where'd you go squared? Boom. And now we got some large numbers coming in here. I kind of wish we were in meters, but that's okay. 71,111. And that should be millimeters per second squared. You're going to see, I think, unless I screwed something up. Oh, no, I see. Okay, this was given as meters. Okay, so that would be 4,000. Okay, at least it's close to the range. I was about to say, this thing is going to get killed by the other thing. It's going to be dwarfed. Like, not even going to matter that it's there. It's going to be so small. But let's see. I'm going to give myself some more paper. I don't like squeezing stuff in. I actually think squeezing stuff in hampers my ability to solve things. And I've seen people that just try to squeeze everything as tight as they possibly can. And I don't know if that's like a comfort thing. Like maybe it's like it's giving it a nice hug. I don't know. But to me, that like this chaotic brain already is trying to stay in line. Squeezing the thing together makes my head spin. But anyway, okay. So I have that one portion, and I'll show you why this is. This becomes the difficult kind of acceleration problem, but I'll do it. But I'm just going to mention that there's a little bit of a. You got to stay focused to be able to do this one. So let me draw in the three diagrams. Just go ahead and do that of the link BC, and then explain myself. Don't have to explain myself without the. Hopefully I'm making them about the same size and same orientation. Kinda, not terrible. This one got long. All right, so what we were given in the beginning of the problem was the acceleration here is this way. So this is the known. So this will become the reference one because we know everything we want to know about it. So we will put in that same thing in both locations, this one and that one, and then that means we're going to pin it right there. This one, we actually know a little bit. So we should try to use that. It's going to be in this direction right there. So I'm kind of tempted, yeah, we will go ahead and put both of these in there carefully. So we have that one. I'll try to make it look like it's perpendicular because it is. We have this one, and we recognize that we don't 100% know that that arrow's in that direction, by the way. So we have, I hate labeling these, let's just call this, I guess I'll call it AC with respect to D in the normal direction. It gets a little confusing if you start looking at this diagram, but that is what we've called it onto the other page, so we might as well call it this. This is acceleration of C with respect to D in the tangential direction. I'll come back to that here in a second. So this is going to be acceleration of B, which is equal to 4 meters per second squared. So here's our acceleration of B, acceleration of B. All right, so now we have this one, and we know there's going to be a normal acceleration. Once again, and this is a great example of what I had said previously, where you're going to have two things that you don't know, and you don't know the direction of either of them. So don't guess anything but positive, and you're going to be okay. Start guessing the negative thing, you could really start messing yourself up. So we go this right here, and we're going to go this alpha. This is the thing that we're trying to find, CD, and this is a guess in the direction. So if we're going to draw that in that direction, it would be this guy right here, acceleration of C with respect to B. Okay, yeah. I had to think a second for that. And that's going to be tangential. Here's the acceleration of C with respect to B. Normal. The acceleration of C with respect to B. Normal. We can find that with omega BC squared LBC. And it's going to be the same value that we had for the other one. I know it's confusing because we have the same length and we have the same angular velocity. That's going to come out to the same thing, right? So you're going to have a 15.40 squared times 300. And I think the professor who wrote this problem and asked for this probably thought that this would make it like a faster problem, but I think this problem's too long, personally. Not to get judgy, but I'm judging. And I haven't used it's not funny in the context. It was funny to me. I used to say all the time, I don't judge. I observe and mock. But I don't judge. I'm not judging you, but I'm making fun of you to your face. All right. What else here? Okay, so I'm not sure where the right place to put this is, but what Natalie had suggested before is probably best to break the thing up into components. Break this up into components with some unknowns, right? So hopefully I won't confuse you too much with that right there. Then I'm just going to go, what is the acceleration of C in the x direction, and what's the acceleration of C in the y direction? By doing that, I think you'll make it kind of obvious how it'll make it a little easier. Still challenging. Because I have this value already, but I also know and I didn't give myself a good place to put it, unfortunately. I'm going to write it right in there and sneak it down below. C, with respect to D in the tangential direction, is simply going to be alpha CD times the length of this, which is 300. Okay, so in the, let me see, I got to put this in here. Here is 60 degrees. Is that where I want to put it? Yeah, and then I'll put it here. This is 60 degrees. I just don't want to get it all mixed up here. So don't erase on exams, he said as he was erasing. Acceleration of C in the x direction equals 0. Acceleration of C not equals 0. Here we go. All right, so acceleration of C at this spot, according to this, remembering that this is a guess, in the x direction is going to be 71111 times the cosine of 60 degrees, right, plus alpha CD times 300 times the sine of 60. So what you end up with, I should have left myself some more room. 71, I already have that right there. Let me go, 60 times cosine. So you're going to get 35556 plus, and I'll put something, so 60 times, oh, Jesus, come on, stop. Sine times 300 times 259.8 alpha CD. Should have picked another problem. And then over here in the y direction, we're going to get 71,111 times the sine of 60, right? Because it's the opposite. It's opposite from the angle going up that way. And then, but then minus, and then alpha CD times 300 times the cosine of 60, because that's that component right there. Problems that have this like kind of feature to it are inherently kind of not impossible. They just require a little bit of diligence. And so that's going to be 61,584. And then minus, and then this would probably be 150, right? But I'm still doing it anyway because I don't trust myself. Trust issues, 150 alpha CD. All right, so I do that because it's going to be easier when I go down to this spot right here to figure this thing out. But it is going to be, this is going to be a condition where we have two equations and two unknowns, and we're going to have to do some solution. It's kind of a pain in the ass. But anyway, until right here, here's the 60 degrees for this one, and then that means that this right here is 60 degrees. It'd be easier to use the 30, but I'm going to stick with what I have right there. And then that is going to be alpha C BC, alpha BC times also 300. Okay. So we write out the equation that we need to know right here. The acceleration of C is going to be equal to the acceleration of B plus the acceleration of C with respect to B, tangentially plus the acceleration of C with respect to B in the normal direction. And then we start to proceed across. Now we already have I've already broken these into x and y's over here. So in the x direction, and there's not this one. This is the problem that doesn't have the luxury of getting rid of much stuff, and so you actually have to do a simultaneous solution onto the thing. But in the x direction, we had 35,556 plus 259.8 alpha CD is equal, so that came from right there. This has the acceleration of B, which was 4,000 positive. And now we're going to have this is going to be in the negative direction. This acceleration of C with respect to B, negative times the cosine. This is not a great example because of how difficult it is. But hope I haven't lost people completely on this. It's not, it does make it seem like this is a tough problem because of these additional features. All right, so that was negative because it's going to the left. This one we made an assumption that it was going counterclockwise, so that this will have a positive x value right there. I ran out of room, so I'm going to put this down here. I'm going to go alpha BC times 300, and you got to remember to make it with the angle, and it's going to be the sine of 60. And go ahead and collect a lot of the stuff in there. We want to end up with a value, something in front of alpha CD, and then something in front of alpha BC. And you're going to be a little bit careful. I'm going to keep the value on the left-hand side, and I'm going to move CD and omega BC on the right-hand side. So all I have to do for this is just subtract out. No. I have two values in there. So I'm going to have my 35,556. Subtract out 4,000. And then I'm going to add to it 71,111. I'm a little nervous because isn't the cosine of 60.5? Oh, we're going to add that. Okay. So 60 cosine times, yes. But now we're going to add. I think that's right. So I think I got it right. Doing math in front of people, not one of my most enjoyable things. Okay, so on the right-hand side, we could go ahead and have a negative 259.8 alpha CD, and then lastly plus 300 times the sine of 60. So 259.8 alpha BC. To the y direction, there's probably like some massive shortcut that you'll see. We could look this up on the Must thing, and he'll do it like in 3 steps, and you'll be like, "Oh, that's easy. I could do that." You won't be able to do it that way because it's just he found some shortcut. It might be some kind of silly thing. You just memorize some routine. All right, so here, going to y direction, we have 61,584 minus 150 alpha CD. There's nothing in this direction, in the y direction here. And for this one, this is going to be a positive, and times the sine of 60, so it's going to be this thing. So 71111 times the sine of 60. This is also in the vertical direction right here. So then we're going to use the cosine of 60 times alpha BC 300. So it's going to be plus alpha BC 300 cosine 60. And so let's see, what do we end up with? Okay, so 61,584 and 71,111. 60 sine times, that's positive, so we're going to subtract it. Oh, they're equal to each other. Look at that. That one and that's equal to each other. Is anybody else getting that? No? Gave up. Sick of this problem. Hey, I'm trying to be a good role model here. Not with my potty mouth, but stick it. Even though it's a hard problem, just do it. Just do it. Yeah. You don't like doing it, but just do it anyway. Tell you what, that's a marketable skill set, man. Just like a pit bull on a pork chop. Just you look at something that's hard to do, and you're like, okay, I don't want to do that. That's difficult. But then you just go do it anyway. I swear to you, you don't believe me, you'll rise to the top, being able to take care of yourself. But I think that's going to subtract out. You got to say anything? Thank you. So that actually cancels with that. So we're actually, this makes it a little bit easier on some respects. We're going to equals 150 alpha CD plus, and we know that one of these has to be negative, so they couldn't both be negative, but this we had. So we had the cosine is 60, that's right here. So that's, they must be equal to each other and opposite. We just found it out. I said before, I wasn't sure. I wasn't going to make a commitment. I didn't go, no, they can't be equal to. They're equal to each other. All right. Maybe not the next second, but because there's this symmetry, they must be. Okay. So you see that they're equal and opposite to each other. We could substitute back into here and find out what that value is going to be. All right, so let's say that, this guy is equal to that guy. Plug him, or go the other way around. I guess it doesn't matter. I'm just going to keep track of it. My brain's not working at all. So this is how bad my brain's working. I have to write it down. I'm not going to try to think my way through this. Negative 259.8 times, I'm going to replace this with a negative alpha BC. So I get a negative and a negative, and I'm going to go plus, what's the one up here? Where'd you go, buddy? 259.8 alpha BC. So that's going to be positive. So we're going to add, so we're going to take the 67,112 and 259.8 times 2, divide. And we're going to get alpha BC. It's going to be a positive 129.2 radians per second squared. And therefore, alpha CD should be equal to negative 129.2 radians per second squared. That was hard. Man, that took a long time. I need some some tepid, it's cold now, green tea. Dr. Saki gave me this green tea, so it's like authentic. I think not all green tea is authentic. But it had Japanese lettering written on it. So that, I don't know, somehow to me seems, I don't know. You want to do something else? We want to cleanse our palate. We need some sorbet. Why is it? Okay. Okay, because these were both positive up here. So one of them had to be negative. So I decided to put this one and substitute for that one. And when I did, it ended up showing, it ended up being positive. So now it has to be the opposite sign. This one has to be the opposite sign of that one. See, I'm almost like people are leaving. I feel so. I'm feeling like guilt because I know you can't put up with any more of this on your Good Friday. But we could keep on going, and you can see what the recording is. You're welcome. I didn't mean to scare you off. I don't mean it to. This is not a question that someone would ask. Not a sane person would ask on an exam because it's just too long. I mean, no, honestly, this is the kind of problem that I probably would have gone, ooh, this is a good problem, and I'll put it on my draft, and then I would start solving it, and I'd go, oh, no. That seemed like a good idea at the time, but I always practice, because it's like a little trap, because it looks easy, and you might look at the solution and go, anybody can do it, but if you do it in practice, I've learned, you do not give an exam without taking it myself. Thank you so much. Have a great weekend, and happy Easter, and whatever you say it is. I almost said Passover. It's not Passover. It's Good Friday, yes. Wait, decent Friday? Long-winded Friday. Long-winded. You have a question? Okay, so we won't do the velocity. If we do an acceleration, we won't do the velocity on that same problem. You do a separate problem that's a velocity problem, right? Because that just makes the problem like crazy long. Although I do know professors who would only ask one question, make it a really, really long question, but then I don't think it's fair because some students just get like totally stuck onto one thing, and some people have that kind of thought process where they just can't allow themselves to get past something that they can't do, and that's not a good reflection on what their mastery of the material is. It just shows you the insanity of. No. But I would probably let's see a problem that's like almost like more straightforward acceleration. What do you say? No? Yes? No. Everyone's gonna leave me. I should just talk to myself. See, like the last exam 2 review session was not my best work, and I really wanted to like redeem myself in this, and so it was because I went for the ball dropping on the other ball on a string, and I forgot that there was a string there. It was not my proudest moment. I don't know what my proudest moment was, but it was not that. I really thought that must was the way to go, but like you look at that first one and go like, how is it? Actually, I really, 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 really want to look that one up. It's all to see what his answer was. So is that a hard one? Angular acceleration. This one's almost too simple, but I say that and about to be. All right, so here's one where I might consider it. All right, so let me go to the slides. Onto the thing, I can't see it. Right, so actually, let's just do this one. I'm sorry, let's just do that one. I have that right above. I was thinking of doing this one right here. Could do both of them, actually. I think I could do both of them in a short amount of time. This one we want to determine the angular accelerations of CB and CD at this. Actually, this is the same problem, but just with different geometry of that last one. So let's do this one right here. All right, so as you'll recall, I'm in organizing your work. Recognize that there's really 3 sets of kinds of problems. You have this is the one I would call the general motion problem. This is a crank slider or slider crank kind of problem. Someone calling me from Greenwich, Connecticut. And so as I walk through there, I could say, see, this is also a crank slider. This is also a crank slider. There's a crank slider. This is a 4-bar, hidden 4-bar. It's like a crank slider, but it's a 4-bar. They just used a wheel as one of the bars. So you can just kind of ignore the fact that it's a wheel and recognize that it's just like a bar. It's just like, this is a crank slider. That's a crank slider. There's a crank slider. There's a 4-bar. This is also a hidden 4-bar. Right? The wheel doesn't matter. It's just the fact that you can take a look between B and the center of the wheel and just treat that like it's one of the bars. Here's a 4-bar. This is sort of a crank slider. Yeah, you can think of that as a crank slider. Recognize that wheels that don't slip have an instantaneous center of rotation, which is the interface between the ground and the ball. This is a general motion problem. Even though it might look like a crank slider, but it's a general motion problem. Really a general motion problem. You kind of see that these linkages are going to be symmetrical, so they kind of move outwards right there. So, crank slider. This is also a crank slider. Crank slider. Crank slider. You get the idea. And this was a crank slider. This is sort of like an instantaneous crank slider, but I'm starting to. Actually, that's a trick problem. I think this has Coriolis in it. So what the hell does that mean? Well, it's if a linkage. No, it's not. Okay, this is a crank slider. Sorry. Coriolis will appear if one of the linkages changes length and rotates at the same time. And while as this changes length right there, it doesn't rotate, so it's not. Anyway, bar, crank slider. So you get the idea that you want to try those problems out. The problem is when you're making a problem sufficiently doable in the amount of time that you have. 4 bars are hard to do for acceleration. They take up a long time. And then you also just saw that even a crank slider, given which direction that you're going without any simplifications, because of the fact that it was at an angle right there. I'm sure the people from must have, so I did that, went ahead and used that simplification to greatly shorten the problem. But you have to know ahead of time to do that. But here's the general motion type of thing. It's usually got really just one effective link that'll make any kind of difference. All right, so and it's at 45 degrees. So this is, honestly, I think that 45 degrees is sort of a cop-out when creating a problem. Because it doesn't measure whether people can figure out what the angles are. So 300 millimeters. And they're saying that the velocity VA is 1.5 meters per second, whereas acceleration A is 16 meters per second squared. What are we trying to do here? Find, I didn't measure, this was 45. 45 degrees. Find AB and alpha AB. All right, so you need to know the angular velocity of it first. Find that fairly quickly. Doing the ICR. Should be the same right in here. They don't. It doesn't actually. It doesn't even really matter. One of them doesn't even matter. Just to find out the first one. So you go R A I C R. Guess I should have labeled that A and then B. And so R A I C R is just going to be either the sine or the cosine. Doesn't matter. 300 cosine 45. So you get 212.1. These are millimeters. Yeah, the dimensions are millimeters, but these are meters. This is millimeter. Okay. So you can find the omega of AB. Going to be VA over RA ICR. So 1,500 divided by 212.1. .071 per second. And now we go to the acceleration. So we do should have done this something like this first. Chased away all the people. Shoulda, woulda, coulda. Live with regret. Okay. Acceleration of A. So put it at both spots. That our acceleration has to be either up or down. And we're going to have this thing, AB. This is my get. I'm guessing that angular, that direction. It's going to be acceleration of B with respect to A in the normal direction. Here's my acceleration of B with respect to A in the tangential direction. Acceleration of B equal to acceleration of A plus the acceleration of B with respect to A, tangential, plus acceleration of B with respect to A, normal. In this case, actually, the x direction is going to be our buddy, our good friend. So we'll go the x direction first, because it starts out with 0. And then we're going to have a value of 16. I'm going to stick with millimeters, 16,000. And in the tangential direction, noteworthy, we don't really care which one is 45, that one or that one. But technically speaking, they told us this was 45 degrees right there. So therefore, this would be 45 right up there. Oh, no, wait a minute. Sorry. My bad. This would be 45. I'm gonna stick to my guns and do the right one. But obviously it doesn't matter. If that's 45, this has to be 45, and then this is 45. Now we know that is actually 45, but in terms of like what was given, those are the ones that match. So we're doing tangential first, and that is in the negative x direction. So we're going to go negative, and that's going to be alpha AB times the length 300, and it's going to be the sine of 45. And then this component is going to be negative omega squared, so 7.071 squared. Probably should have written that down somewhere. Maybe I could just write it right here. Omega AB squared L AB times L AB is 300, and notably it's going to be cosine of 45. Alpha AB. Let's see. All right, so I'll start out with my 16,000. Should have used that guy right there. I'll flop him around and go square him. Square, where'd you go? Square, there, square. Ooh, turns out to 50. Okay, that's good. Okay. 300. Boom. 45. Okay, so that's negative. Adds to that. Plus. So now we're going to, this is going to jump over on the other side. And we go 300. Sine, divide. I get a positive 125.4 per second squared. Anybody? Nobody? Okay. Let's take my word for it. Yeah. So we're going to go in the y direction. So does that make sense? Well, first off, I'm going to ask myself, does that make sense? Makes sense it's going to accelerate counterclockwise. If the bottom of the thing is accelerating to the right, it makes sense that it's kind of going counterclockwise to me. All right, so I'll buy that. You get 25? Just 25? I wonder how that happened. Mystery. And then this one, we know we're just going to have the acceleration of b because it's just going directly up and down. And there's nothing from this diagram, so we're entirely over here. So I'll start out with this guy, and so that's going to be our alpha 25.4. And the diagram, by the way, is going upwards, so we're positive. 4 times our 300 times, and let's try to using it accurately, it's going to be the cosine of 45. And it's very common for, if that one's sine, this one's cosine, and so forth, and vice versa. And this one is also, this is going downwards. This guy is going downwards in the normal direction, so it's negative. And still 7.071 squared, 300, and sine of 45. Acceleration of b should therefore be, so 25.4, 3 sine, boom, 7.071 squared times 300 sine. And so interesting, I got a negative number. Did you get a negative? Interesting. So That's always puzzles me, where you could have it looks like it's not possible that you would be accelerating to the right at the bottom, but this one's slowing down. But I guess that makes sense. It's really, a lot of times it would be, I think I might have pointed it out in a class where, no, actually it was in my mechanisms class. When it comes to the angular, it comes with any of the accelerations, but especially the angular one, a lot of times it's some of that acceleration is, well, I don't know. I'm trying to enunciate four things at the same time. It's deceptive because it's the speed changing, or it's the direction changing. But this is all speed changing, right? There's no direction change. It's not on a. There's no curvature to this. And okay, so it could be moving fast, but it's still decelerating, so it could be going the other direction, right? So it's like accelerating this way, but this one already had its maximum amount of acceleration and hit its maximum velocity, and now its velocity is slowing down, right? So this one's speeding up at the bottom, this one is slowing down because it already went fast. And now it's going not as fast and not as fast while this one's getting faster. Does that make sense? So it really messes with your head because you want to think of it in the same terms as velocity, which you can actually see, but you can't really, you can perceive that it's accelerating, but you can't really quite see it. And it doesn't match the direction of its motion. So that's a good problem because it's, like I said, I don't like the 45 part, though. Say that I want to see vector stuff done, and is this giving too much away? No. Usually the general motion is a good place to see the vector approach. Find this using the vector approach. And then, so, vector math approach. Do I keep doing another one, or are you exhausted and want to go home? It's non-committal. All right. Okay. Let's see. Let's pick a problem that can be done simply. How about we try to do this one? So here's determine the acceleration of collar C if rod AB starts from rest at the position shown and has an angular acceleration. Okay, well, this is almost too easy because it has no velocity component to it. Yeah, I'm sorry. We should need to pick up something else. That was a little... Just trying to see something that's going to be doable. Let's see. That previous problem in vector math, if you want to do it. Or something more exciting. All right. Nah, come on. I want to. I gotta do something with something in it, right? What was that noise? I'm tired. Let's just do this one. All right. All right. So what they had shown us in this problem, I need to. What they had given us in this problem was that the velocity was equal to negative 1.5 I, and that's an A, and then the acceleration was equal to 16 I. I guess I should do meters per second and meters per second squared. We could tell that the velocity of B is V as a vector, sorry, vector heads. VB in the j direction. The acceleration of B was in the j direction. And the only thing else that we knew was that this thing, we knew what the length was. So what we're really trying to find initially, we need to know what the angular velocity is going to be. So we'd say that the velocity of B is equal to the velocity of A plus omega AB K crossed with R B with respect to A. B with respect to A. So what you say that VB, and we needed RB with respect to A. So let me write out. So we're looking at B from perspective of A. It's a little too easy. And say, we're going to do it in millimeters, so these others will be larger numbers. 300 times the cosine of 45 I plus 300 times the sine of 45 J. And so they're going to be equal to the same thing, right? 45 cos 300, boom. 212.1 I plus 212.1 J. So when it comes to the velocity, applying all of these things that we know, we have VBJ is equal to negative 1,500 I plus omega and AB. I guess won't be lazy. It's supposed to be cross product. I feel like being lazy, tired. So do the distribution of this of omega AB times 212.1 K crossed with I plus omega AB 212.1 K crossed with J. This is going to be J, and this is going to be negative I. I don't need to rewrite the thing, but you could, but it just takes time. But so you could just go, okay, what do we want to do? Let's do the I direction first. 0 is going to be equal to negative 1,500 minus, I did that right? We're going to minus omega AB times 212.1. Trying to remember what did we get before. It should be now. There's going to be a negative number, right? Does that make sense? No, it doesn't make sense. What did I do wrong? I'm losing it, man. It should be, oh, that's because it's going to the, it makes sense. Yeah, it makes sense. I'm sorry, yeah. Because it is. It's going to the left. That's going to the left. So it's going to go clockwise. All right. And so omega AB is going to be 1,500. So same thing we got before, right? radians per second. And now we do the same thing, but we want to, we don't need the J direction, right? Because they didn't ask for VB, right? The question wasn't asking for the velocity of B, or did they ask for the velocity of B?
It was acceleration.
Well, yeah, they just wanted the angular acceleration. Oh, yeah. So we didn't need the velocity at B. We could find it though, like easy from here now. So we could go like in the J. So we might as well do it completely. VB was equal to nothing there. It's just going to be this right here, right? So it's just going to be negative 7.071, and it kind of makes sense that it's going to be going downwards. And it should end up equaling the other value, right? It should be 1,500. Because if that's moving that way, this one should be moving that way, especially since it's 45 degrees. Right? The acceleration, you take the acceleration of B is equal to the acceleration of A plus alpha K crossed with R B with respect to A minus omega AB squared times R B with respect to A. So we know the acceleration of B is only in the J direction. It'll be equal to the acceleration of A, which is 16,000 I, positive direction, plus, we could go ahead and write this out as skip this little step. We kind of know, we've been doing it a bunch of times, right? So you go, I'm sorry, this would be LB. Alpha AB times 212.1, and that'd be K crossed I, which we know is J, plus alpha AB 212.1 K crossed J, which we know is negative I. I still didn't be able to fit it in there. So coming it back down, I don't know what that means. Minus, we don't need to put a negative sign in there. We could, but it doesn't really matter because we're squaring it. And 212.1 I minus 7.071 squared 212.1 J. Remember, we don't have to cross product this one. This is just this negative times this value squared times this thing right there, and just stretch it, put them right in there. So if you collect the, there could be a strategy. I think once again, just do the I's, because we leave out one of the unknowns, and we're going to be able to isolate the alpha. So if you do the I's as part of this, you have 0 equals 16,000 plus, no, let's make it minus, because you have your minus from there. So this one, I know they look alike, but we're going to use this one because we're using the I's. So we'll go to minus right here and go alpha AB 212.1. All right, so we have that right here, and then but we also have this guy in here. So we're going to have minus 7.071 squared 212.1. 16, 7.071. About in there? It's squared, yeah. I can put them in there. I'm with you. Usually a good idea to do that. So, 25. Did it end up being negative? No. I think it's 25.46. Really? I think it has to jump over. This one has to jump over to the other side, so it gets rid of that negative. This one was bigger than that one, right? So anyway, go back over to J and go there. Equal to nothing from right here. You get your alpha, which we said was 25.46, plugging it back into there. You're 212.1, and you're still going to subtract out 7.0. I'll put the negative in there too. 7.071 squared to 12.1. Acceleration to B. 212.1 times, and then you get 7.071 squared to 12.1 times minus, I get a negative 5,205. And these are millimeters per second squared. And that should have matched up what we got in the last, in the previous problem. I was off by a little bit. Round off error. I think it was the 25.46. I used 25.4 in this one. So I'm blaming you. Okay, well, maybe I dropped something along the way. I'm tired. Hopefully that helped to some extent. I don't know. Practice more problems, challenge yourself. Yes, yes. Some instructors might not, but I would ask you to do which one. I'm sorry, I spoke over you. I didn't mean to. I haven't decided yet. I'm gonna put together something. Sometimes I said this earlier that my priorities are to measure ability to do vector math, right? That's a solid problem. Ability to do the 3-diagram method, and ability to do the ICR. And I might mix it up as to whether it's, that 3-diagram method is acceleration, but chances are it's going to be and also that there's the outlier, because sometimes there's not enough time, so I might not ask a problem with it, but I may, depending on my, as I work through the things, I go, oh, look, it rarely happens, this abundance of time. I also want to see if you could do angular kinematics, which surprisingly students struggle with. I'm not making a judgment. I am surprised by that. All right, thank you, and have a great rest of your Good Friday, and an excellent Easter. May all your chocolate bunnies be solid instead of the hollow ones, which always seemed like a ripoff to me as a kid. See this big old bunny, this huge bunny, and it's just this thin little thing of chocolate. It's just not. You put your jelly beans in it. True. That's, hey, you know what? That's a bright side. You bright sided that. I'm exciting things. That's a good bright side.
Thank you, Dr.
I think I need to stop recording. Yes, thank you. Appreciate you too.